Have you ever looked at a number and just had absolutely no idea what it really meant? You know, a test score, a weight, some kind of measurement? On its own, it's just a number. But what if I told you there's a simple little tool that can give any number, anywhere, immediate and universal meaning? Well, today we're diving into exactly that. We are talking about the Z-score. So, let's start with the basic problem here. A single score all by itself is pretty much useless. It's kind of like hearing one single note from a piano without knowing what song it's from. You just don't have any context. So let me ask you this. You take a test, you get a 76. What's the reaction? Do you celebrate? Do you, immediately start cramming for a retake? The honest to goodness answer is, you have no idea. Not yet. Because that 76 is just kind of hanging there in space. Okay, now look at this. This is where it all starts to make sense. We're giving that 76 some much needed context. Now, in both of these graphs, the average score, the mean, is 70. But just look at the difference in the spread of all the other scores. In the graph on the left, everyone's scores are packed super close together. A 76 here? Wow, it's way out in the top tier. You're an absolute rock star. But now look at the graph on the right. The scores are much more spread out. And that exact same 76 is, well, it's smack dab in the middle of the pack. It's totally average. Same score? Two completely different stories. And this, my friends, is where the Z-score comes swooping in to save the day. Think of it like a universal ruler. It's a tool that lets us measure any score from any test in any situation and understand its true meaning in an instant. It completely solves that context problem for us. So what is it really? A Z-score takes those two key pieces of context we just saw, the average and the spread, and uses them to turn a raw score, like our 76, into a brand new standardized score. And this new score, it tells you exactly where that original number stands in the whole lineup. And here's the beautiful part. It's so simple. A Z-score gives you just two little pieces of information. First, the sign. Is it positive or is it negative? Well, if it's positive, you're above average. If it's negative, you're below. Easy. Second, the number itself. That tells you how many standard deviations you are away from that average. So it's not just if you're different from the crowd, it's how different you are. And the engine behind this amazing little tool is a surprisingly simple formula. Seriously, don't let the symbols fool you. It's really just two basic steps. So here's how you do it. First, you take your score and subtract the mean. That gives you the raw distance from the average. Step 2, you just divide that distance by the standard deviation. That's it. So for the example here, if your score is 130 and the mean is 100, you're 30 points above average. Then you divide that 30 by the standard deviation, which is 10, and you get a Z-score of +3. Simple as that. All right, now we're getting to the Z-score's real superpower. Because when you use this little formula on an entire set of data, not just one score, something kind of magical happens. You standardize the whole thing. So here we have a typical population of scores. It's got its own average, a mean of 100, and its own spread, a standard deviation of 10. This could be anything, right? Test scores, heights, weights, you name it. And bam. This is what happens after the transformation. We've converted every single one of those scores into a Z-score. Now look, the whole distribution has shifted. You can see it kept its original shape, but now it's centered on this new universal scale. And this leads us to 3 golden rules. Every single time you do this, 3 things are guaranteed to happen. 1, the shape of the distribution stays exactly the same. 2, the new mean will always be 0. And 3, the new standard deviation will always be 1. Every single time. It's a rule. What we've just created is called a standardized distribution. And because any set of data, no matter how weird or different, can be converted to this common format where the mean is 0 and the standard deviation is 1, well, it means we can now compare things that seemed totally impossible to compare before. So let's put this universal ruler to work, shall we? Let's say we have to compare 2 students who took completely different tests, the classic apples and oranges problem. Okay, here's the challenge. Sarah gets a 620 on her SAT, and James, he gets a 26 on his ACT. I mean, on the surface, those numbers don't mean anything next to each other. So who actually performed better compared to everyone else who took the same test? Z-scores to the rescue. Let's take Sarah's SAT score, 620. We know the mean was 500 and the standard deviation was 100. A little bit of math gives her a z-score of plus 1.20. Okay, now for James. His ACT score was 26. The mean for that test was 21 and the standard deviation was 5. That gives him a z-score of plus 1.00. Suddenly, the apples and oranges are on the exact same scale. And just like that, we have our answer. Crystal clear. Sarah did better. Her performance was 1.2 standard deviations above the average on her test, while James was just 1.0 standard deviations above average on his. The z-score just cuts right through all that confusion. You know, you've probably experienced this yourself. Anytime a teacher or professor says they're grading on a curve, this is basically what they're doing. They are standardizing all the scores to see how everyone did relative to the rest of the class, instead of against some absolute standard. It's z-scores right there in the classroom. And this isn't just for school tests. This idea is everywhere, doing some really important work, often hiding in plain sight. Let's circle back to IQ scores for a second. That entire system is built from the ground up on a standardized distribution. The mean is purposefully set at 100 and the standard deviation is set at 15. So when you hear someone's IQ score, what you're really hearing is a rescaled z-score that tells you precisely where they fall on that famous bell curve. Z-scores are also absolutely critical in scientific research. So imagine some scientists are testing a new growth treatment on lab rats. They start with a whole population of normal, untreated rats, and they know the average weight and the spread. After giving the treatment, they measure a rat's weight. So how do they know if the treatment actually did anything? Well, they calculate its z-score compared to the original group. If a treated rat has a z-score near 0, it's probably just an average rat. But if its z-score is extreme, let's say it's way up past plus 2.00 or way down below minus 2.00, that is a massive signal. It means that rat is now so different from the original population that it's almost impossible for it to be a coincidence. The treatment very likely had an effect. This right here is the very foundation of inferential statistics. So you see, the z-score is way more than just a formula in a textbook. It's a way of translating data into a universal language that everyone can understand, from your report card to major scientific breakthroughs. So the next time you see a number or a statistic, just ask yourself, what's the context? Now that you know the secret language of data, where are z-scores shaping your world?